Hello calculus students, this is Mr. McAllen and this is a video recap of the other day in class where we were working on limits involving infinity. So we first started out the class where we did a do now where we worked on these standardized questions 71 through 76. So if you were not in class, you should try to give these problems a try. And what we first did was I had the students work on 71 and 72 and then we discussed them. So I'm just going to write pause up here on the video. So you pause the video, you try them out. When you unpause the video, I'll have the answers for you and I'll go over it. Okay, so we're back and the first question is really asking what is, if the left-hand limit, because of this little negative sign here, of a function equals 2 and the right hand limit also equals 2. Now what this basically means is you have a function that as you're getting to C, it's heading to the same value from both sides, the left and the right, and because they're heading to the to the same value, pardon me, then the limit as a whole exists. So as x goes to C, the function's limit does exist and it equals the same value. In the next question, you're supposed to do a little bit of limit algebra, and by limit algebra I mean you want to break the limit up, so you're just going to break that fraction up into x over x plus the limit as x goes to 0 of the sine of x over x. And as we discussed yesterday, if you get 0 over 0, you should try to simplify, and this limit simplifies to where the x's cancel and you're left with 1. And the limit on the right, we discussed in the video before, in class the day before, that the limit as x goes to 0 of sine of x over x also goes to 1. So our end result of this limit is in fact 2, and this answer is true. Now, I want you to try these problems on your own. I'm going to pause the video, and these are basically how you evaluate left hand, right hand, and whole limits with the piecewise function. So work on those and I'll put up the answers and then we'll move on with the lesson. Okay, so we're back and we're going to work on these piecewise functions. So take particular note that we're looking at as x approaches for 73, we're looking at as x approaches negative 1 from the left. So that means we're going to use the function that signifies values of x from the left. And by theorem 2, we can just plug in, when we're approaching 1 from the left, we can just plug into that top equation, and that limit will be 2 minus 1, or 1. So that would be choice C. For the same reason, for the next one, we're going to use the bottom function, because that would be values to the right of 1. The plus after the 1 means from the right of 1. So that limit, as x approaches 1 from the right, would be plugging in 1 over 2. I'm just plugging right into the limit as theorem 2 says in our book, and that would equal 1.5. Now, because they're asking for the whole limit in the third part, in 75, we would say that does not exist because the left-hand limit doesn't equal the right-hand limit. And the last question is, what is f of 1? Well, you plug 1 into the function, and as a result of plugging 1 into the function, you would have to use the top function, and this would equal the value of 1. What did we do in class yesterday, or on the day when we started this lesson 2.2? All these materials are from Finney, Demana, Waits, and Kennedy. They're calculus book for AP Calculus. That's redundant, but this is the book that they write for AP Calculus. And the objectives that we're working on today was we talked about finite limits as x approaches positive and negative infinity. We talked about the sandwich theorem, and then we talked about end behavior modeling. So this video is really for the purpose of catching up on these topics. And so what we first did was we talked about a limit, or looking at a graph of a function that we know pretty well, the hyperbolic function. We have f of x is equal to 1 over x, and as x approaches or heads towards an infinite value, we see the y value is heading to 0. So as x heads off to infinity, the function value is heading off or trying to get to 0. And this can be represented by a limit. and this is a limit as x approaches infinity. You write in f of x, and that would equal 0. Now, in pre-calculus, what we talked about was if for this type of a function, we would draw a dotted line that would be a horizontal asymptote, and that would be y equals 0. Well, in this lesson here, what we're trying to do is tell students or show students that horizontal asymptotes basically are described with our new limit notation. So this would represent the function as f of x, where f of x is going. Let me just clean that up. Is heading as x is growing to be very, very large. Or x is heading to infinity. So these are two, basically these are two statements, two limit statements that define a horizontal asymptote. The next thing we did was we looked at this example 1 from the textbook, and I stressed to the students that notice that it asks us to use graphs and tables to analyze this function. A lot of times when you look in the book, you may not know whether to use graphs or tables or do it analytically. That means basically with using your just the skills you have with pen and paper and no calculator or no technology. But in this case, they want us to actually look at graphs and tables to find the limit. So what I suggest you do is on your graphing calculator, plot, or on Desmos, plot exactly what it says here and analyze what the function is doing as x is heading off to infinity and x is heading off to negative infinity. And I'll give you a moment to do that. I'm going to pause the video, and I'm actually going to put Desmos up with that function so that we can discuss that in the next scene. Okay, so I'm back, and I plotted the function, as you can see over here on the left. And if you look at the graph, you could see that the function, as I just scroll with the dot here, you could see that the value of the function as x is getting bigger, you see how x is now at 2.8, 3.5, 4.8, the value of y is heading towards just the value. If we keep pushing the graph till further and further, see how we're at 30, 40, 50, the value of the function is only going to get to 1. It's not going to go above it. And if I move the graph over to the other way, well, I should write down what that limit would be. So here I'm just going to write down, so the limit as x goes to infinity of f of x is in fact equal to 1. And if we analyze as x goes to negative infinity, we look at the same graph, and I move back and back and back, you see that in this case, as I probe on the function with Desmos, as great as x gets, my y value is going down to negative 1. So I'll capture that with a limit statement. And this is analyzing a limit graphically, and I could have done the same thing if I'd used a table on my graphing calculator, but in this case I just did it graphically through Desmos, and we did both in class. We used both tables and graphs, so you should know how to do that, or you should do that or be able to do that when we have a quiz. The next example that we had was we talked about this limit again, or this quotient again, but in this case we were talking about the limit instead of x going to 0, we were considering as x goes to infinity for sine of x over x. And this forced us to have a discussion about what's called the sandwich theorem. Now I'll basically put the sandwich theorem in layman's terms, but the sandwich theorem basically says, because I know what the sine of x is a limited function as x goes to infinity. The sine of x only varies between 1 and negative 1. It's a bounded function. So it stays within these values. So as a result, I can make an educated guess that my numerator is not going to get any greater than 1 or any less than negative 1. So I'm going to consider just the case where I'm at a value of 1 for the numerator, but I'm going to evaluate the limit as if I let x go to infinity, and I'm going to make a educated guess as far as what my limit at infinity would be if I sandwich the top value. As a result, if grows to be very, very large, this limit is going to go to 0. And this can be verified graphically, but this is kind of a thoughtful way to work through the limit instead of just jumping right to technology. So I'm going to put on Desmos, I'm going to change the function, and I'm going to put sine of x over x. So I've got to find the sine function. There it is. Sine of x divided by, just have to move over a little bit and divide by x. And if we look at that function, I have to zoom in because, or go back to, alright, now if you look at the very beginning, yesterday we were talking about how as x approaches 0, we get to a 1 value. But if you look at the sine function, how it wavers at first, and then eventually, as x goes out to infinity, the value of the limit heads to a 0 value. So that's what we predicted when we were looking and when we were thinking about the sandwich theorem for the numerator. So, in our next example that we worked on in class, we challenged students with the idea of how do you find the limit of this complicated function and as x goes to infinity. Well, the same laws that we had with limits before when we were going to fixed values apply when you're going to infinity. So, as a result, we're allowed to take this limit algebraically and we're allowed to break it down. So I'm just going to break it down into two pieces, kind of like what I did earlier in the lesson with the warm-up problem. I'm going to take this and turn it into 5x over x plus the limit at infinity of sine of x over x. Now from the previous example in the sandwich theorem, I know that this limit is going to head to 0. But this limit, because of the cancellation terms, I know that the limit as x goes to infinity of 5 is going to equal 5. So the end result of my limit of this part and this part is going to end up being a value of 5. The last thing that we talked about in class was the idea of end behavior modeling. End behavior modeling is where you consider the function at its ends. So if you have a function and you're looking at the both extremes of where x goes to infinity and negative infinity, what you're allowed to do is look at the most dominating polynomial in the numerator and compare it to the most dominating polynomial in the denominator. Those functions, as x heads to infinity, will have the loudest voices. And as a result, this entire function can be represented by just, as you can essentially make the argument that as x goes to infinity, for this complicated function, really the only thing that would be noticed for this function as x goes off to a large, large value would be the highest term polynomial in the numerator and the highest polynomial term in the denominator. So you just consider a limit between those values, making the algebraic approach much, much easier. So this can only be done as x is heading to positive or negative infinity. As a result, I'm really just applying a limit to as x approaches infinity to 2x squared. And as a result, my end behavior model, so my end behavior model would be the function 2x squared, or something that looked parabolic. So, hopefully this video has helped recap some of the main points that we had in class, and I look forward to hearing your comments, and please comment on this video on YouTube whether you're in the class or not, and let me know if these concepts make more sense to you now. Thank you.